invisible friends, hello and welcome back to our series on electrical and computer engineering. Tonight we continue our conversation on Thevenin equivalence. In our previous movie we introduced this great idea of two geniuses, the Frenchman Leon Thevenin and the German scientist Professor Hermann von Helmholtz, that if we have a linear network and we care only for what happens at the terminals of that network when it's connected to something else, we can model that linear network only by two elements, one resistor, RTH, and one voltage source, VTH. And we said that it was sufficient to determine the value of VTH and of RTH to perform two tests on that circuit, an open circuit test and a short circuit test, and that was fine. On paper it was. Because you see, in the real world, in the lab, short-circuiting the port of a live network may not be such a great idea, don't you think? That's why tonight we introduce two alternative methods to determine VTH and RTH, two methods that do not require a short circuit test, the two resistors method and another method that I came up with years ago for the sake of my students at UBC, the UBC method, the two current sources method that my students sometimes nickname the 1 amp 2 amps method. Now, without further ado, let's begin.
Let's have a second conversation on the Thevenin-Helmholtz equivalent circuits, because it does not end here. Previously, we have seen how Helmholtz and Thevenin and Meyer and Norton, they came up with this wonderful idea of replacing a linear circuit with a simplifying equivalent circuit that has only one source and one resistor, VTH and RTH for the Thevenin equivalent. And we have seen that to find the value of that source VTH and that resistor RTH, we need only two tests, the open circuit test and the short circuit test. In the first one, we measure directly the value of the source VTH, and in the second one, we measure or we compute on paper with M&A what is the value of the short circuit current, and with that we compute what is the value of the resistor R Thevenin RTH. Measuring the open circuit voltage of a port is fine, and we can even do that in a laboratory, but short circuiting the port of a live circuit may not be such a good idea, no. Today we learn other methods that we can use to find those two parameters, the two resistors method and one method, the two current sources method, that I call sometimes the UBC method, because that is a method that I myself concocted for the sake of my students here at UBC. It does not need a short circuit test, which is something that's been given grief to many students I've known over the years, and secondly, it applies perfectly to the HP50G, which is an equipment my students here at UBC use. In the classic method, we perform the open circuit test and the short circuit test. We take the circuit and at the port we compute using M&A, or in the laboratory we measure with voltmeter what is the open circuit voltage VOC. Next, we short circuit the port and determine the value of the short circuit current ISC. In a real-life circuit, as I said, short-circuiting a circuit port may not be a great idea. In those real-life circuits, we can use this alternative and safer method. Open circuit test, we measure the open circuit voltage, and that is VTH directly. That is fine, same as before. But next, instead of short-circuiting the port, we apply a resistor with a known value of our choice, RA, and once we connect that to the port, we measure the voltage that appears across the resistor, VA, or we compute that with M&A. And then what? Well, think of it. In the actual circuit, we connect a resistor, let's say RA, and then we measure what is the voltage VA that appears. If that circuit and this one are truly equivalent to one another, when we connect the same resistor RA to this port in the equivalent circuit, the same voltage VA must appear. Where do we know that VA from? From the real circuit on the left. We measured that voltage in the circuit on the left, and we know that should appear on the circuit on the right. The current that flows is given by Ohm's law, VA divided by RA. That current will produce a voltage drop in the resistor R Thevenin, and that will be given by Ohm's law, RI. R Thevenin multiplied by the current, VA divided by RA. Now we can write a KVL equation around that loop, going up by Vth, going down by the drop in the resistor Rth, and going down by Va. We can rewrite the equation this way, where we have moved the known term Va to the right. In that equation, we know Ra. Of course, we chose it. We know Va. We measured that in the lab in the circuit on the left. And we have two unknowns, Vth and Rth. So we have one equation, two unknowns. We need another equation. If we have performed the other test as an open circuit and we've already determined who is Vth, we can simply solve for Rth, and we have Thevenin obtained from the open circuit test minus Va, the voltage that we measured in this resistor test, multiplied by Ra divided by Va. But let's say that we do not do an open circuit test. We just apply a second resistor. In this case, we need another equation. Pick another resistor Rb and connect it to the port. Measure the voltage Vb that appears and apply that to the equivalent circuit. Again, the same analysis for current, for drop in R Thevenin, and for the KVL equation. Another equation, same unknowns Vth and Rth. We have now two equations and two unknowns. Let's write them together. From the first test, Ra, and from the second test, Rb. Two equations and two unknowns Vth and Rth. Piece of cake. As I said, if we've already done, instead of applying a resistor for the first test, we apply an open circuit test, then we find our Thevenin directly with this simpler formula. Tutorial time. Let's say we have a circuit, and at the output port of that circuit in the lab, we connect a 3 kilo ohm resistor. A voltmeter at that port reads 3.75 volts. The resistor then is replaced by a second resistor with a value of 6.2 kilo ohms, and the voltage at that port changes to 5.536 volts. The question is, of course, find the Thevenin Helmholtz equivalent. Find Vth and find Rth. 3 kilo ohms is Ra, is the value of the first resistor, and the voltage that appears is Va, 3.75 volts. So 6.2 kilo ohms is Rb, and 5.536 volts is Vb. Write the equations, solve for Vth and Rth, and next we draw the equivalent circuit. That is the solution to that exercise. Are we done? No, we are not done. This exercise is for your entertainment, even though it's not properly related to what I've said. Now let's concentrate on my method, the two current sources, the UBC method, right? In this method, we work on paper, not in the lab. We apply to the port of interest a current source. A current source with a value of our choice I sub A, like so. When we do that, of course, a voltage will appear at that port. Let me call that voltage VA. That's going to be a number from a voltmeter. In reality, on paper, a value that we compute with M&A. If that circuit is truly equivalent to this one, when we connect that current source to the equivalent one, the same voltage VA that I have obtained with M&A from the circuit on the left must appear. Now that current IA of the source must produce a voltage drop in that R Thevenin with the value Ri, isn't that so? RTH, IA. And with those three voltages, we can write a KVL equation around the loop, going up by VTH, going down by RTHIA, going up by VTH, going up by RTHIA, going down by VA. That equals 0. Let me move VA to the right hand side. We have one equation where we know IA, the current source value we chose. We know VA, which is the voltage that we computed with M&A in the real circuit on the left. And we have two unknowns, VTH and RTH. Of course, what do? We repeat the same exercise, but with a different value of the current source. Apply a current source IB and compute the voltage that appears at the port VB, like this, appears. And we repeat the same analysis to the circuit on the right and write the second equation. We have then two equations and two unknowns VTH and RTH. Let me write them together from the first test and from the second test. Two equations and two unknowns. In general, I can write the M&A equations in the real circuit applying a generic current source IX. A voltage Vx should appear. When we write the M&A equations, we substitute Vx for IA and we obtain Vx is VA. And then we edit the same equations and change Ix for IB and obtain that Vx this time is VB. We can get away with writing the M&A equations only once and solving them twice. They are different only in the values IA and IB. Not clear? Okay, let me show you an example. In this circuit, I apply a 1 amp current source. Could be any value, I chose 1 amp. And then I compute what is the value of V1A. How? I write some M&A equations like so. And solving that M&A equations, I obtain the voltage of Y, which is V1A. That is V1A. Y, 5.571 volts. That is IA, 1 amp, the current we applied, and VA is the voltage 5.571 that appears across the current source when I do that, when I connect that source. Now repeat that test with a different value of the current source. I will use just 2 amps, just because it's easy. And to find the voltage that appears V2A, that is VB, we write the equations. Observe, the 2 amps current source appears here in the M&A equations, right? Current entering to node Y, to the second node. Solve and find that the voltage that appears in the 2 amps current source is 6.694 volts. That is VB. IB 2 amps, VB 6.694. We have now 2 equations and 2 unknowns. Please observe one thing. Let me write side by side the M&A equations for the 1 amp test and the M&A equations for the second test with the second current IB, this one. You notice that they are just the same. The only difference is the value of the current source. So what? Well, that if you write those equations in the HP50G like so, you see where the 1 amp is there in the second equation. We can just solve the system, find what is the value of VA, and then once we have that written on paper safely, we undo, swap, down arrow, and edit that equation and change the 1 for a 2, enter, swap, solve again, and find the value for VB without having to retype the M&A equations. Those are the equations, right? And the solution is 4.178 volts and 1.393 ohms. That is the equivalent Thevenin Helmholtz circuit for that network. A variation of the two currents method is one in which we use IA equals 0, which turns out to be an open circuit test, and VA would be the open circuit voltage, which is just Vthevenin, right? We use IB, then any value. In this case, let me use 1 amp, and the equations turn out to be this one, right? IA is 0 and IB is 1. Observe, easy equations. VA is Vthevenin and Rthevenin is just VB minus VA minus Vthevenin. Sweet. And you're thinking, well, wait a second. A 0 amps test is just an open circuit test, right? Then why do you call that a 0 amps? Because then I use the same symmetry of equations for my calculator. That is all. That is all. Nothing magic about that.
Now, this is your turn to practice. Consider this case. A student performs the two current sources method tests, and he measured VA and VB as follows. He was using current sources with values 3 milliamps for the first test and 7 milliamps for the second test. It is very important for this problem to observe that he connected the sources and the voltmeters this way. For the first test, he connected the current source IA right side up, flowing from B to A, and the voltmeter upside down, with the black probe on A and the red probe in B. The values were 3 milliamps applied right side up, and he measured in the voltmeter that is connected upside down negative 38 volts. For the second test, he connected this time the current source upside down. It's flowing from A to B this time, but the voltmeter he kept upside down with the black probe in A and the red probe in B. The values are 7 milliamps, and he read 32 volts in the voltmeter. What is the question? The question is, with those readings and the values of the current source and the polarities and directions that we have seen he used, when he writes the two equations that are necessary to find Vth and Rth using the two current sources method, and one writes those equations instead as a matrix equation like this, what should be the coefficients A11, A12, A21 and A22, and also what should be the values of VB1 and VB2? Think about it. Once you've thought about that carefully, you'll come up with this result. Ready? This one. The matrix on the left-hand side is 1, 1, 3 millis, and negative 7 millis. Please observe that this is the current IA of the first test, and that current source was a right side up. That's why this coefficient appears as a positive one. In the second test, 7 milliamps upside down. That's the source of this negative sign. On this side, I have VA on the top and VB on the bottom, but the voltmeters were upside down. That's why the signs need to be reversed. And once we solve that system of equations, we get Vth 17 volts and Rth is 7 kiloohms. The lesson from this example is that one has to be mindful of the polarity of the current sources and also of the voltmeters, because both may change the matrix and both may change the right-hand side vector. Let's have a look at a particular case, the 1 amp, 2 amps method. If one chooses a 1 amp for the first test, apply that right side up like that, and measures with the voltmeter connected right side up, like so V1A. And for the second test, we apply a 2 amps current source right side up, and the voltmeter is also right side up to measure V2A. Then the system of equations can be written in matrix form this way: 1, 1, 1, 2. And V1A, V2A on the right-hand side. Of course, this 1 is 1 amp flowing from the bottom to the top, and this 2 is a 2 amps flowing from the bottom to the top as well. I am assuming, when I write positive V1A and positive V2A, that both voltmeters are right side up. And that is the 1 amp, 2 amps method that you've seen me using in the tutorials in this series. By the way, if your resistors are in the kilo ohms range, I recommend that you use 1 milliamp and 2 milliamps instead. And of course, the matrix would be 1 milliamp, 1, 2 milliamps. And that is all my invisible friends. I hope you have enjoyed or at least profited from watching this video. I hope to meet you again in our next movie.